Hello, welcome to another talk on this channel. Today I will talk about adversarial machine learning and digital watermarking. This is a talk that I gave in 2018 as the keynote of the ACM workshop on multimedia privacy and security, which was co-located with the CCS conference. And since we are now all sitting at home due to the outbreak of the COVID virus, I thought it might be a good idea to take the old slides and just record the talk again, so that you can have fun with it and see what I've been talking about 2 years ago. I didn't change anything on the slides, so maybe I'm looking confused at some point. That's okay. It's kind of a retrospective view on this keynote presentation. So I started the keynote with some introduction about myself. Since this is a YouTube channel devoted to my institute, I'm skipping this slide and I say, well, if you're interested and do not know anything about us, please visit the URL that you can see there. And also, when I was at CCS in 2008, I had the feeling that people do not know where and what TU Braunschweig is. And maybe you also don't know. So TU Braunschweig is a university in the middle of Germany. It's in the city Braunschweig. And Braunschweig is the origin of many cities in the world that are called Brunswick. So the English translation of Braunschweig is actually Brunswick. And if you think of New Brunswick, then basically I'm working at Old Brunswick. And the location is here. And it's in the middle of Germany. And the place is very close to a very famous automotive vendor. And a lot of our collaborations, of course, are with Volkswagen. So typically my group is working on applying machine learning in different contexts of security. So we're interested in detecting attacks or preventing attacks. And we have done some work on analysis of malicious software, Android, JavaScript. We did Flash analysis when Flash was cool, or only half dead. Now it's completely dead. And we also did a lot of work on finding vulnerabilities in software. But for some strange reason, we did something completely different a couple years ago. And this talk will be about this experiment or this adventure. And this adventure is about bringing machine learning, adversarial machine learning, and digital watermarking together. And first of all, let's look at the two topics and see how different they are. So first, machine learning. Machine learning is really a trendy topic. It's a super active area of research. And in 2008, there have been about 3,000 papers submitted to Arxiv that cover machine learning related topics. I'm not sure whether Arxiv is a good metric for measuring importance of research, but it's clearly a measure for trendiness. The more there's published there, the more trendy the topic is. And you see 3,000 papers is really a lot. And there are some really cool applications for machine learning. Here are just 3 examples. Autonomous driving, autonomous vehicles, like maybe even drones or spaceships, these cool virtual assistants that we can talk with and that order some crap for us or useful stuff. And of course, something like fraud and intrusion detection, malware detection, and so on and so forth. And then we have digital watermarking. It's a branch of multimedia security. It's a classic area of research with a history of more than 20 years. And it's driven by a small research community. In contrast to machine learning, it's not a very big field anymore. And if I looked into Arxiv in 2018, there were only 5 papers related to digital watermarking. So it's a little bit a lost research space. And maybe some of the cool findings in this area are now overlooked because it doesn't get the focus that it maybe used to get 10 years ago. There are some applications for digital watermarking. Most of them are not that cool. So for example, copyright protection, tracking of users, and verification of authenticity. But nonetheless, personally, I'm maybe not a fan of these applications, but they make sense. And of course, they also have a place in the world of security because authenticity and finding copyright violations are very security-related topics. So the question is, how do these two things fit together? And that's actually an open question. And they have fundamentally different objectives. So one is about learning, creating somehow intelligence. The other one is about marking objects and tracking them. And then we have the fuzzy world of machine learning with all the uncertainties and probabilities. And then we have the exact world of watermarking, where we want to say, this is almost like a cryptographic proof almost. If this watermark is present, there's almost no chance that it came in randomly or by some other event. And thus it's a proof that this has been owned or marked by somebody. And so far, there has been almost no connection between these different worlds. Until 2012, I would say, when Erwin Quiring, a PhD student in my institute, joined our group. And Erwin came from the lab of Rainer Böhme in Innsbruck, and they have a focus on multimedia security and also a little bit on digital watermarking. And I took Erwin and said, you have to do all the cool research in our institute, like applying machine learning to different topics. And from time to time, he would say, yeah, this is all cool, but what about digital watermarking? Some of the stuff you are telling me about adversarial learning and attacks has already been done in this area. And to be honest, I ignored this for some time. I said, yeah, I don't know, no idea. Don't bore me with this old stuff. But after a couple of repetitions, I said, well, Erwin, if this is really something, then let's do a joint project here and try to bring the things together and see whether we can write a paper on these two topics and whether we can work out their similarities. And maybe there's something bigger, something interesting. And it turned out that this was a very good idea, and Erwin did excellent work. And we came up with a pretty cool paper that in fact joined the two areas. And this talk is about this family reunion. So bringing the two together and seeing what they share. And I hope I a little bit whetted your appetite, because I'm now diving directly into it and see what's going on. And to do this, of course, I have to first start with what actually is machine learning and what is digital watermarking. And you can imagine, if you're giving a keynote talk, you do not want to bore the people in the audience. So I decided to make something like two very quick, in a nutshell, description of the two areas. And if you are an expert in one of the two areas, then please be gentle with what I'm telling now. It might be on a very high level. Maybe it's not super correct at all the edges, but it's kind of the best thing that I could come up with in a very short and condensed form. So first of all, what is machine learning? So machine learning can be said it's a theory and also a practice of making computers or computer programs learn in a very broad sense. And in its inner part, it's mostly about finding dependencies in data. Sometimes people talk about finding patterns, but I would say it's more about these dependencies. And the dependencies, they create a link between the input and something that you want to learn. And we do not want to just memorize the dependencies, so just store the data or something, but instead we want to generalize them. So we want to find general patterns that map from some input domain to some output domain. And we call this learning if we can apply the resulting system on unseen data. It takes the input and it predicts the output that we want to have. And to give you an example of how I imagine this, let's look at handwriting recognition. So you can see in blue some written text. It's text that I once wrote. It's a little bit ugly. It's not easy to read. And on the back, you can see in gray the concrete particular letters here. So the L, the E, the A, the R, the N, and so on and so forth. And now the task of a machine learning algorithm is to analyze these two representations, start with the input, the written shapes, and try to find out what is the dependency between a written shape and a particular letter. So for example, if you see something that looks like a circle, there is a dependency between a circle and an O. Or if you see something that looks like an A, so it's a shape that is similar to a circle but has some kind of, I don't know, edgy thing on the side, then there's a relation between this shape and an A. And ideally, a machine learning algorithm picks up these geometric representations, these shapes, and learns dependencies to the concrete letters. And then it can automatically do the mapping, and this would correspond to handwriting recognition. We can write this down a little bit in a boxology way, so in a kind of boxes representation. So we have this data, which is our written shapes, and we have the labels, which is the concrete letters. So we here have a 5, an 8, and a 5. So this is the labels, and the written shapes would be the data. And now the task of machine learning is to infer a model, theta. So this is the colored thing there in the middle. And this theta represents the relation between the two things, x and y, the dependencies. And then we can apply this learning model, theta, to unseen data. This is the new 8 in the bottom. And then we can apply the dependencies and get a prediction. This is the digit 8. And we do this using a prediction function f, and this function f is parameterized using this learning model theta. This is the most basic and simple form of describing learning. Maybe you're surprised there's no neural network and there's no random forest or support vector machine, because it's one level above the concrete learning algorithms. The algorithms basically construct these learning models theta, and depending on their origin, these theta models could be a neural network, could be support vectors, or could be the trees in the random forest. But we are one level above this, so for us it's sufficient to have a function f that takes an input and returns a prediction from the space y. And the most common example of applying this concept is classification. Classification is about categorizing objects from the input into a set of given classes. And it's a very popular form of learning, so it's used in street sign recognition, it's used in handwriting recognition, it's used in image content recognition, and so on and so forth. It's supervised, so we are training with data that is labeled, so we're training with examples that are categorized into the known classes, and we try to learn a function f that predicts whether an object is in one of the classes. And here we can see this in a geometric way. It's a simplified example. Instead of looking at a multi-dimensional, high-dimensional space as typically is used in learning, we take a two-dimensional example. And we assume that in our two-dimensional world, we have these different written shapes. On one side, the 5s, and on the other side, the 8s. This is our feature space, our input space. And now the task of learning is to find a function f that separates the objects in this space. And in the two-dimensional case, this is pretty simple. It's just some line that goes through the space, and on one side there are all the 5 digits, on the other side there are all the 8 digits. And of course, in practice, this is a high-dimensional thing. The function can be very bumpy. It can have thousands of different dimensions and local and wave-like minima and maxima in its form. In this example, it's just a simple 2D, and it shows the function f. You will later see why this is important for this talk. Of course, as I said, this is just a simple example. Even in 2D, you can have different variation of this prediction function. It can be quadratic. It can be a neural network with some bumpy structure. It can also be something like decision stumps. This is the basic of random forests and decision trees. So then the function is a little bit more edgy. But overall, a lot of machine learning is about learning a function to classify data. So let's look at digital watermarking. And I will start here with the original digital watermarking world and then slightly move into a similar representation. And I guess in 2 slides you will see, oh, there's really something similar. So digital watermarking is about embedding a pattern, a watermark, in a signal. Often this is done in images. but it can also be done with audio or video or any other signal. So it's a generic technique for adding a pattern, a watermark, into a multimedia signal. And this pattern should be imperceptible in the case of vision, or it should be inaudible in the case of audio, and it should also be inseparable. So it should not be easy to remove the watermark from the signal, because then somebody could just remove it and have the original signal. Still, this pattern should be detectable. So these are the three kind of most important goals that we have here. We want to add the pattern. It should not destroy our signal. It should not be perceptible. It should be inseparable, but still we should find it. And of course, what we want to achieve is that this whole system remains robust, even if we transform the data. So if we think of an image, we might compress the image. The watermark should still be present. And here I'm showing as an example a super simple watermark. I'm not an expert in digital watermark. This is why I chose a very simple example. So you have the original image on the left, X. This is Lena. I have to say this is maybe not state of the art, because this Lena image has a kind of strange story. So I apologize for not noticing this when I prepared the talk in 2018. It wasn't even okay in 2018, but next I should put Fabio there. So there's another picture showing a guy, and maybe it would be better to have a guy here or something neutral. Anyway, we go with Lena for now. So this is the image X, and now we add noise to this image, W, and this is our watermark. And the trick is that this noise is super fine-grained. It's happening at the level of individual pixels, and it has a very low amplitude in the signal. So it just adds a very fine layer of noise to the original picture, and you cannot see it in this version. Even if you would zoom in now, it is not visible. You have to be very close to the image, see the individual pixels, and maybe then you can spot something, but it's very hard to see it. And the process is similar to machine learning, but not exactly the same. So here the idea is we have the signal on the left. This is our original image, X. We have the marking process where we add our W, and then we get something that is called X tilde, which is our marked signal. This is the process that is created maybe at a company, at a movie company that gives out images or movies, and they want to have a watermark in these movies such that they can track copyright infringements. And then later, if they find a new signal, a new image, they can do a detection phase, and they use the watermark pattern, so this raw watermark, and check whether it is present in this signal or not. And they use a function that I call G here. The G takes an input from the input domain, and it says yes or no, depending on the presence of a watermark. And what is similar to the learning model here is this watermarking pattern W that is transferred between the marking and the detection stage. Now we can also phrase this as a geometric thing. There exist many different algorithms and schemes for watermarking data, and they are technically very different from machine learning. But we can assume that the data we have lives also in a high-dimensional vector space. This is not called feature space here, but media space. But of course, a pixel can be seen as a matrix. It can also be seen as a vector if you stack the columns of the matrix on top of each other. And thus, an image is also a vector. And similarly, other forms of media like audio or video signals can be represented in a high-dimensional vector space. And thus, watermarking these signals corresponds to moving around in this vector space, because you change them, you add, for example, the watermark on the signal, and thus you get this X tilde. This is why I'm showing here a small arrow. So if I'm adding the watermark, somehow the signal changes a little bit. It stays visually the same, but the content is slightly different. What we need now is a detection function. And this function is also something that is related to machine learning, because it is a function that lives in our media space And on one side, we have all the watermarked images, and on the other side, we have all the unmarked images. So that is, ultimately, this is closely related to a prediction function. In the case of the prediction function, we had two classes, left and right from the function. Here we have unmarked and marked signals on both sides of this function. So this is where the relation comes into play. And I guess we can also have these different functions, of course. And I guess you see, well, if we now put the two together, then maybe we can gain something from this. And at first, when I talked with Erwin Queering about this, I wasn't really convinced because I said, well, there is some similarity, but many things in the world have similarities. So why would we gain knowledge from this? And Erwin said, well, we do not need to look at what's going on in the original algorithms, but we need to look at attacks against the algorithms. And it turned out that attacks against machine learning and digital watermarking are closely related. So let's look at what attacks are. Well, if you have a learning algorithm and you deploy it in a real-world scenario, somebody might try to trick on this algorithm. And the research field on finding these attacks or defending against these attacks is called adversarial machine learning, and it has a history of about 10 years. There's a cool article by Battista Biggio and Fabio Rolli, and they present an overview of these 10 years. And it's a good read because it covers all the different research directions and the different attacks that happened in this time and have been developed over these 10 years. And then we have digital watermarking. And funnily, digital watermarking is inherently adversarial. So whereas machine learning lives in a peaceful world originally, and only in the last 10 years has moved to the bad, hostile reality, digital watermarking has always been in the adversarial world. Because if you add a watermark, you do this in presence or view of an adversary, because somebody wants to remove it or do not want you from tracking him. So the history of attacks in digital watermarking is as old as research, and it goes back at least 25 years. And there's a cool book by Cox et al. That you can have a look at that covers all of these algorithms for watermarking, but also always attacks that can break some of these algorithms and defenses that protect from these attacks, and so on and so forth. The attacks, of course, have different names in the digital watermarking world. Maybe they are called oracle attacks or estimation attacks, whereas in machine learning, some attacks are called evasion, poisoning, membership inference, and so on and so forth. So the worlds are not connected, but both have attacks in them. And now let's try to see whether we can bring them together. And we do this with two little tricks that are obvious after the first part of the talk. The feature space is very similar to the media space. So we assume now that we are in a vector world, and if we're doing machine learning, it's a feature space. If we're doing watermarking, it's a media space. Simple. The same holds for the classifier and the watermark detector. Both, we assume now, are binary functions. So we abstract it a little bit and assume that in machine learning, the classification task is binary. This is a common simplification. And we say, well, on the one end, we have the binary classifier that has two sides. On the other end, we have the watermark detector that also has two sides. And both operate in the feature space, media space. So this is all the same. And if we now conduct attacks, either against a watermark detector or against a classifier, we can look at what is actually happening. And if we start with this box view, we can find location where the attacks are happening. So for example, we could say, maybe we can play with the input and try to mislead either the learning or the watermark detection. In the machine learning world, this is called an evasion attack. In the watermarking world, this is more often called an oracle attack. But we can also look at another location. So can we infer what's inside the learning model? Something that is called model extraction in machine learning, and that is called estimation attacks in digital watermarking. Here the idea is I'm trying to steal the model, or I'm trying to steal the watermark pattern. And as you can see from the picture, the similarity now is very obvious. And let's just look into the two cases and let's try to find out how these two attacks are working. So an evasion attack or oracle attack, or nowadays often called an adversarial example or adversarial input, is a very small perturbation of an object X that tries to mislead a classification or tries to mislead a watermark detector. So the idea is I'm looking for a small t. I'm using some distance function d to measure that this t is small. How this d is chosen is up to the concrete attack setting. And if I add this t to my x, the prediction function f makes a wrong decision. It's called y star here because typically if you add a star to a variable, you imply this is the goal of something. And if our goal is to have a wrong decision, then we would call this y star. Of course, there exist many different ways of constructing this attack in practice. So it depends on the knowledge you have. Then it could be white box, gray box, black box. It also depends on the style. Are you working with gradients or are you working with some kind of discrete optimization? So there are many ways of conducting this attack. But in principle, from all of these differences, there's some joint thing, and this is that you move the x in the feature space across the border of the function f. So all of these attacks have the goal of misleading a function, and misleading means moving something onto the other side. And in the case of adversarial examples or evasion attacks, we want to move it, but at the same time do not change a lot of the visual appearance or of the content. And this is why here in the example, I'm moving the 5 to the wrong side. Now it becomes classified as an 8, but it still stays visually a 5. And to illustrate this, I programmed something. And already during the keynote talk, I said that if a professor is programming something, well, you cannot expect too much. This has many reasons. I think the most important one is a lack of time in the professor job. Also a lack of skill sometimes, but that's a different story. So I implemented an attack. For both settings, I used the same attack. So I'm implemented an attack against digital watermarking and against machine learning, and it's a very, very simple attack. So let me explain how the attack works, and then we look at an animation showing how it proceeds. So the attack is the following. I take the image of a 5. I go through all of the pixels and add a little bit of color to it, or I remove a little bit of color from it. And whenever I'm doing this, I'm measuring, am I moving towards the decision function? So I add a little bit of, let's say, brightness to some pixel, and I'm checking, does it move me into the direction of the decision? So does it move me in the direction of the 8? Because I want to flip the prediction. And I do this for all pixels, and then I pick this pixel that has the highest gain, that moves most to this decision function. And then I repeat and look again for a change. And the only thing that I do here as a trick is once a pixel has been changed by 10%, I'm not touching it anymore. I'm doing this because otherwise it might be that there's one very large white pixel in the picture and it would look disturbingly, and it would also somehow violate our idea of having a very small perturbation that is not perceptible. So let's start the algorithm. And what you can see now is, if you look very closely into the video, there are some gray spots now in the image, and the image moves closer and closer and closer and closer and closer to an 8. And at some point, which is now, it is classified as an 8, although the visual structure has not changed at all. This is a typical adversarial example, and it's computed with a very simple greedy algorithm. Super simple, to be honest. And let's do the same thing on the right side. So here we have a 5. It's not a machine learning task, it's watermarked. If you look very, very closely, I'm not sure if you can see it. It has a watermark pattern in it. So there's this kind of noise in the picture that marks the image. And now I'm doing the same thing. I'm changing the brightness or the color a little bit of each of the pixels, not more than 10%. And at some point I cross the border and now the image is not watermarked anymore. Or to be honest, or more precise, it's watermarked, but the watermark has been destroyed, which means the detector cannot find it anymore. So you can see, same algorithm, same attack, two different areas, works. That's great. So let's look at model extraction. Can we maybe do the same thing here? So model extraction, watermark estimation. It's a little bit difficult to describe this attack in a formal way. I try to do it here. Nowadays, I would do it differently, but let's go with this way. So I'm saying I'm looking for a small number of inputs, U, such that if I train or learn or generate a prediction function from these small inputs, I can minimize the distance between the original function f and my stolen function fu. So what does it mean, a small set of inputs? So basically I'm querying the original system. So I'm sending queries, inputs to my original prediction or watermark detector, and I'm recording the output. And I try to do only very few of these queries and get the best outcome from it. And the best outcome would be a function fu that is very close to the original function. So you can see in the picture, the idea is like sending queries very close to the decision boundary and then walking along the decision boundary such that you get a very good estimate of it. And there exist, again, different strategies for doing it. As I said, this is maybe not the best way to describe it formally. One reason is that the attacks have kind of very different objectives often and are not formalized in this way. But still, underneath, all of them try to reconstruct a function by sending a few queries and learning from these queries. And again, I programmed a toy example. And again, it's a very simple example, but it's the same algorithm for extracting a watermark and extracting a learning model. So first, let's look at the case of the learning model. So here we can see a true learning model in a linear version. So this is the linear support vector machine. If you know what a support vector machine is, it is a hyperplane separating two classes. And in the linear case, this hyperplane can be described by one vector, which is a vector describing this hyperplane. So typically it sits on this hyperplane in an orthogonal vector, as an orthogonal vector. And if you colorize it and say everything that points towards one class and is green, and everything that points towards the other class, so everything that is positive is green, and everything that is negative is some red color here, magenta style, then this is in fact a classifier separating 5s from 8s. The first interesting thing that you can see here, by the way, is the classifier has not really learned the shapes as we maybe would expect. It has learned those pixels that are related to the classes. And maybe we can see something in the middle points towards the green class and something outside the middle points towards the red class. And now we do the following. We do a very simple model extraction attack. We send random data to the classifier and see whether it is classified as 5 or as 8. That's really simple, right? And the only trick that we do is these vectors, these random vectors that we throw at the model, they are orthogonal. And if you remember one of the first parts of your math studies, if you studied math or some area where math is important, if you have a linear system and you throw orthogonal vectors to the linear system and you get the output, you somehow are constructing an orthogonal basis. And this enables you at a certain point to exactly define all the variables in your linear system. I think it's even done in school that way, not with the names of orthogonality. I think it's called linearly independent then, but technically it's the same thing. And you can even do a least squares approximation if you have only a couple of these orthogonal vectors. And this is what I'm doing here. So I'm throwing the vectors at it. And the number of the iteration number basically is the number of vectors I'm throwing. And you can see after maybe 300, 400 vectors, I get a very good approximation of this learning model. And after 779 queries, I get an exact copy. And this is basically the result. We have here in this example, I think 770 or 80 pixels. So this means we have 707 variables in the model. And thus we can prove that after so many iterations, after so many orthogonal vectors with output, we have perfectly reconstructed the model that is StolenNet. In practice, let me start this again. I would say already after, let's have a look, 400, 500 examples, this might already be a stolen model that works very well. If you now say, hey, that's 400 queries, that's a lot. Yes, it's a lot. It's a simple algorithm. But this has been trained on 10,000 examples of digits, and I stole it with a fraction of the data, less than a tenth. And this, if you are a company and producing this model, this could be painful that somebody is stealing it in that way. Now let's do the same thing with the watermark. And since the watermark is typically not visible, I'm using an example here where the watermark is super visible. So it's a little bit cheating because watermarks should not be visible. But imagine it would be behind an image. Then we would also have the same effect that throwing these orthogonal vectors against the watermark detector slowly, but also after 600 iterations, can extract the watermark. So again, the same attack algorithm works against the two different areas. And when we did this, and we did this with real watermarks and real machine learning models, we were really satisfied because we found something that wasn't known at that time. And in this enthusiastic moment, we said, hey, let's take also defenses from the two areas and see whether they can be applied on the other side. Now, defenses is another topic in security. There's a long tradition in developing defenses in digital watermarking, whereas not so long tradition in adversarial machine learning. But unfortunately, in both areas, no strong defenses are known. Now that this keynote is 2 years old, I would say we have moved a little bit forward, but I wouldn't still say that there's a strong defense. This is a tough problem and there's ongoing research. And I have the feeling that it will take a long, long time until we understand the problem better. I'm not even saying that in 10 years we will have strong defenses. I'm not sure. But I think we will have such a good understanding that we can say under which conditions a defense is strong and under which it is rather weak. And why it's so hard? Well, it's because the attacker in this scenario has full control over the input data. In both the attacks I conducted, the attacker was controlling the inputs arbitrarily. So he or she could make arbitrarily changes at the different pixels. And as a defender, this is a very difficult situation because I'm bombarded with different information. And all of this is under control of the attacker. And often, an attacker has also direct access to the prediction function. So for example, if I have a vision system in a car, I can even reverse engineer it or extract the hardware and work with it. But even if I cannot, I can go to my garage and put images to the system and try to see what the system is predicting. And at that point, the defender has no control over the system anymore. So the system is under full control and in the hands of the adversary. And now he or she can start to push data through it and see how things work. And that makes building defenses very difficult because they would also be now in the system or the control of the adversary. So there have been different ideas of designing defenses. So the first one was to add complexity. And everybody who's doing cryptography knows that adding complexity can help, but very often you get a false feeling of security because you as the designer think something is complex, but it might be that the attacker can outwit your complexity and get something very simple. So there have been many ideas like adding fractals, for example, to this function and make it super bumpy and with many small edges, or obfuscating also this curve with obfuscated gradients. It didn't turn out that this is a good strategy. And before I say why, let's look at another defense which can be beat with the same strategy. So another idea was adding randomization. So instead of having static functions in machine learning or digital watermarking, the idea is that you add noise to them. And this noise is added dynamically. So in each analysis phase, you add different noise to your decision. You could add noise to the features as well. But you still have to keep the noise in a certain range because otherwise your system will make wrong predictions. And in both scenarios, complexity and randomization, the attacker can approximate a function that is less random and less complex, but still matches somehow the true decision function. There's some kind of boundary here or uncertainty where the attacker cannot not infer the exact original decision function. But as I said, both the complexity and the randomization cannot be arbitrarily large. They need to be only that large that the original decision is not changed. And this means that you can always find an approximation that lives within this room and still allows you to conduct attacks. Because here, the attacker just needs to infer the red function, launch attacks against the red functions, and if the attacks are far enough from the blue curves, which would be the dotted lines here, they will also be adversarial examples or destroyed watermarks. So that's unfortunately not a strategy. And then there's one idea that has not been pursued much in machine learning, but which is a classic in watermarking, and that is called stateful monitoring. So instead of looking at each input individually, the idea is that I'm monitoring the inputs to my system, and I try to associate inputs from one user to another. So this requires, of course, that users are somehow part of the system, so I have a notion of what a user is. But if this is possible, I can track the inputs of one user, and I can look at the inputs and see whether they have some unusual relation. For example, here in the picture, if the input of the user are slowly moving towards the decision function, this might indicate an attack. Of course, this can only be done if there is something like a user. It cannot be performed if the system is in the hands of the attacker, because he can then disable this tracking. So it's only possible if this is a remote system. And it, of course, requires authentication and binding of identities, which are challenges in its own. And you can have something like Sybil attacks, where multiple accounts are conducting the attack, and you as defender do not see these attack stages, even though you do stateful monitoring. But that's at least some defense. And we tried now to bring the two things together and see whether we can have some case studies where we transfer attacks or defenses from watermarking to machine learning and the other way around. And let's look at these two case studies that we did. So one is taking an attack strategy from machine learning and apply it to digital watermarking. And the other idea is take a defense from watermarking and apply it to machine learning. Again, the defense that we're looking at is not perfect, but I will show you in the next slides that in both cases, the things are transferable, which shows that our joint idea of having attacks against machine learning and digital watermarking enables one to transfer the attacks, but also transfer defenses. So our first case study was an evasion attack. And we tried to take a recent attack from adversarial learning, in particular the Kalini-Wagner attack, which is at least even in 2020 now still one of the state-of-the-art attacks against neural networks. It's also a simple attack and powerful attack, so this is something that I like. And we would take this attack and throw it against a digital watermarking scheme. And we picked the watermarking scheme Broken Arrows. It was I think, a winner in a watermark competition called BOSE. I think this is called Break Our Watermarking Scheme. It's a cool idea to have these competitions. And I'm not sure if it was not broken, but it was at least a good watermark in this field of competitors. So it's still, to my knowledge, considered a strong digital watermarking technique. And we do everything as said previously, but now in reality. So we learn a neural network that tries to substitute the watermark. So this is called the substitute model. Then we apply the attack from Kalini and Wagner on this neural network and take the output again and see whether it still contains a watermark. So here's what we did. We took images from the Dresden image database, which is a famous database in multimedia forensics. 30,000 images were marked with broken arrows. 30,000 images were unchanged. Of course, the sets were disjunct. And then we partitioned everything into training, validation, and testing, as you would do it in a classic machine learning experiment. And then we trained a vanilla deep neural network with a couple of hidden layers. I even don't know how many layers we used. Not so many. We took marked and unmarked images and tried to learn a neural network that can classify whether the image is marked or not. It worked very well. And then we could, of course, apply machine learning attacks against the neural network and see whether they also remove the watermark. And here's the result. So on the left side, you see a marked image. It's already a cut out region, so it's zoomed in. In the middle, you see our attack there, where the watermark has been removed. And on the right, you see as a baseline a denoising attack, where you just apply denoising to remove the watermark. As I said, it's maybe not the super best attack you can come up with, but it's an attack purely in the world of machine learning, and it works to some extent in the digital watermarking world. We get an accuracy of about 82% here, which I think is pretty cool. And visually, the attack adds a little bit of noise to the picture, but it's not as destructive as the denoising. Let's look at the second watermark. Second case study and watermark transfer. Here we take an attack from machine learning, the so-called model stealing attack from Trama et al., Usenik Security 2016. And we try to defend against this attack with a typical strategy from watermarking, which is stateful monitoring. So what we do is we define so-called security boundaries in our world. So that is, if we have a decision function, we position around the decision function a margin. And if we see multiple queries, inputs within this margin, we assume that this is an attack and then block these inputs or return random answers. So this is a strategy that has been done for watermarking since 2015. And we just take it and try to see whether this helps us in stopping a model stealing attack against a decision tree. And since a decision tree has an edgy decision function, we get something as shown in this picture here. So our function is not some curvy line, but it's some very edgy thing. And the blue points are our queries. The red points are attack queries. And these light blue areas are our security margin. So what did we do exactly? We replicated the experiments from Trama et al. So we conducted model stealing on 5 benchmark data sets where we had trained a decision tree. And we conducted the experiments with and without our defense. So we monitored the inputs to these 5 trained classifiers, and we checked how often inputs hit our security margin and when we had to make a decision for stopping the attack. We did an additional experiment, I will talk about this later, where we even hide the the queries from the attacker in some fake inputs. Because you can imagine this is an adversary setting here, just running the experiment once and proposing a defense and testing it is not enough. So it is necessary to also see how could an attacker circumvent the defense. And what the attacker could do is, of course, try to send 40 normal queries, then send one attack query, 40 normal queries, one attack query, so he can hide his or her inputs in some benign inputs. We did far more in the paper, so this is just a summary. And since the talk is already 2 years old, I'm not 100% sure if I have described everything correctly here, but this was our rough setup. And here are the results now in a wonderful table. So let's look at the different columns. In the rows, we have the 5 data sets and the 5 classifiers. The first column shows the attack without defense. And you can see the number of input vectors until you have stolen a model that has this accuracy. And you can see here, after about 100 to up to 9,000 input vectors, the attack has stolen the model with 100% accuracy. Now, if we apply our defense, the situation changes. After less inputs, so 40 to 900, the attack is stopped by our defense. So we are basically blocking queries from this user. And at that point, we only have between 90 to 20% of the model stolen. You can imagine if you have a Sybil attack, so an attacker that has multiple accounts, the attacker could now proceed with another account, right? We cannot stop this. This is a problem of multi-user systems that you need to make sure that not one person is using multiple accounts. But just from the setting where we assume authentication and binding identities to accounts is perfect, our attacks works pretty well. Now, what happens if we if the attacker adds cover queries to the inputs? So if he's using only every 40th input as an attack and everything is covered, then the attack is possible. So for example, in the first case, now the attacker can get 100% of the model. But the number of queries, of course, increases. And it increases more even than the factor of the cover queries. Because also the extraction becomes more difficult because there's many outputs that are irrelevant. And you can see here that a lot more of the queries are necessary. And I wouldn't say that the attack is not possible anymore. It just gets more costly. But if you don't know this yet, in security and especially in defending, you also have to accept compromises. If you just go for the perfect defense in research, I wish you good luck. Sometimes you also have to accept that defenses are weak, and it's already a success if they're a little bit stronger than the past. And moreover, of course, our goal wasn't here to kind of develop the perfect model stealing defense, but just show that something that has been developed in digital watermarking works to some extent in the machine learning area. So this brings me to the conclusion of this talk. I think it was already pretty long, yeah? So I'm happy if you're still listening. So I showed you a link between learning and watermarking. And if you look closely, and we did this in this talk, the setting and the environment for watermarking and learning has a lot of similarities. And if you look at attacks, they very often behave almost identical. And what I didn't talk about is all the different attack strategies that also match. I talked about the concepts of the attacks, so I was at a higher level. But if you look at attacks against black box systems or attacks against white box systems, in both domains, very often they have an almost identical algorithm. So there's an equivalence in these two worlds. And this is very beneficial for us because we can take knowledge from one area and apply it to another. And there has been some work that picks this up, not a lot, but some work in the last 2 years. And people are using our idea and our identified equivalence to improve attacks as well as improve defenses. So I like this. And I hope that our case studies and maybe also this talk can further foster this work and spawn new ideas of interchanging ideas between the two worlds. There's more. First of all, my feeling is that if you find these things and you say, oh, cool, typically there's more. This is just the tip of the iceberg. And I would expect if we do more and more analysis of adversarial environments in watermarking, in learning, but also in other areas like in signal processing, in multimedia forensics, in vision, in statistics, in robotics, and so on and so forth. And we do not just immediately jump to those areas where we know what's going on. So if you would pick robotics, do not jump to the machine learning part because we know that machine learning is vulnerable there. Jump to the other parts, maybe to the reinforcement learning stuff or the navigation, or maybe also the planning or the moving of joints and all these things that are more inspired from physics. And if you go to signal processing, don't go to the machine learning part, but go to the signal processing part, the filtering of signals. We have a paper on scaling. We had a paper of, no, we have it in this year, attacks against image scaling, which is a signal processing thing. So if you pick all of these different topics and look at the new areas and see what can an adversary do, I bet that we can find far more systematization here, and that maybe in the future we'll have a more better understanding of what an attacker can do with, let's say, processing systems that process input. Maybe we need to restrict this to vectors or real valued inputs, but I would expect there's a broader theme behind these things that is about analyzing the processing of some form of data in an adversarial environment. And I would be really happy to see more research there. And if you're not doing it, my group is definitely doing it because I think this is super interesting and it's also helpful to create secure systems in a future far, far away. So that's the talk that I gave in 2018. I hope you had fun. When giving it now, I really enjoyed the slides that I made. It's always good to have good slides because then you also have fun giving the talk. I think in now the aftermath, it's a little bit too technical for a keynote. It could be a little bit boring in the middle, so it's more like a lecture. But still, I think the message, or I hope that the message became clear. And that's all for now. Stay tuned for further talks on this channel, and the rest of the day, enjoy your time. Stay safe, stay well, because now it's a critical time, and the best is if we all come out of it very healthy and with fun. See you. Bye.